All right, hello everyone. So I hope you all are doing good. So today the agenda is that we'll be solving a few problems on dynamic programming. And today is the first day, but I'm planning to take up sessions like these regularly, quite frequently. So yeah, it would be around at least 2 times a week, as I have already mentioned in my post. So we can do a lot of different things here in these sessions. But today, since this is the first one, I have just planned a simple problem solving session and we'll be solving two problems based on dynamic programming. I won't be teaching anything, we'll be simply solving some problems. And hopefully, we'll be ending this in around 40 to 50 to 60 minutes, something like that, right? So I've already shared the problems with you guys. I hope you all have at least tried them. And if you've already solved the problems, it's the best thing that can happen. And yeah, so when I'm teaching, at any point of time, if anything is unclear, you guys are free to unmute yourself and ask your doubts. And if you don't want to do that, then you can even just ask your doubts in the comments, in the chat section. I'll be regularly watching that as well. So with that, I think we can start with the first problem. So I shared all the problems on the Discord server. So we can just start with the first problem here. This is called yet another subarray problem. So let's just write it down. Cool. So yeah, let's just read the problem statement and see what we can get from there. So in this problem, we are given with an array of size n. N can be large up to 3 into 10 to the power 5. And we also have two integers, which are m and k. Okay, so the task is that we simply need to find the subarray which has the greatest value of this function. So this function is basically, if you have a subarray from L to R, what this function does is it takes the sum from L to R and then it subtracts this value, that is k times the ceiling of R minus L plus 1 divided by M, from this sum. Okay, and your task is to simply find the subarray that has the maximum possible cost. Okay. Also, the cost of an empty subarray is given to be 0, so the answer will never be negative, that is for sure. Okay, so yeah, the problem statement is quite simple. You have an array of size n, where n is big, so subquadratic or quadratic solution won't be working here. So in probably linear or n log n time, you need to find the value of the subarray, the value of the subarray which shows the greatest value of this function. And the function is simply the sum of all the elements in the subarray. And then you subtract k times r minus l plus 1 divided by m, rounded up. Okay. Cool. So I hope the problem is clear enough. So if anybody has any doubts in understanding the problem statement, you're free to ask. Otherwise, I'll give just 4 or 5 minutes of time to you guys to just think of various possible approaches, and then we can go ahead and discuss whatever comes to our minds. Okay. Cool. So yeah, you are free to take 4 to 5 minutes of time. And in the meantime, if anybody has any doubts in understanding the problem, then you can just ask in the chat. So if anybody has any approaches in their minds or any ideas about how to go about this problem, then you can just freely unmute yourself and even write anything in the chat box. Any approaches or any ideas that are coming to your mind. They don't necessarily have to be related to dynamic programming.
Hello.
Yeah.
Am I,
Hi.
am I audible?
Yeah, you are.
So I think like the second term is always constant for a uh, like if you just take the R and L constant means means the difference is always constant, then that part is constant, and the
Okay.
first part is like The maximum sum, like thing I think.
Okay. All right, I see what you're talking about, but the problem here is that the value of r minus l plus 1 by
Yeah,
m,
yes,
that that's not
that
really a
that is
constant thing, right?
yes, that is vary from like 1 to n. Like the maximum is n and the minimum is 1. I guess r minus
Exactly,
l is 1. R minus l plus
exactly.
1.
Yeah, exactly,
Yes.
exactly. That's true. Right. So that's a good way to think about it. If anybody else has any approaches or any ideas like this, you're free to speak up. Also, notice one thing about the constraints here. So it's always beneficial to just read the constraints very thoroughly. And sometimes the constraints end up giving away the solution. And this probably is one of those cases. So yeah, it's really highly recommended to read the constraints very, very carefully here. You will find something very interesting in the constraints, which might eventually even lead you to a solution. Any other ideas and any other approaches?
Hello.
Yeah. Hi.
I think in this two pointers can also be used with some pre-computation, because for every ln r, if we make some prefix or suffix, and like if some function is there like which increases or
Okay.
some variable, uh, in that like two pointers I think can be used on like till the range like that that function is increasing or decreasing. Till that
Yeah.
time we increase L, and after that we decrease the variables. In that
True.
way, I
Okay.
think.
All right.
Uh,
I see what you're talking
like
about, but let's discuss something about two pointers. So this is again something that might be very helpful to you guys. So just as a side note, we can discuss this. So one very basic condition for two pointers to be true is uh, two pointers can be applied in problems like this. So for example, let's say you have an array, okay, and so let's say the array has a property that any subarray starting from an index I and going to an index j is good if and only if any subarray starting at index I and ending at index k greater than j is also good. Or maybe a reverse property is that any subarray starting from I and ending at j is good. Then it implies that every subarray in between is also good. Something like this. Okay. So these are two basic properties in which two pointers can be applied. But there is no such property here in this problem. And the reason for that is this function r minus l plus 1 divided by m is very, very arbitrary. Okay. And even the values in the even the values of the elements of the array are not positive. So this sum function in fact is also not increasing. So neither the first property nor the second property is true. Okay. So that's the reason why we can't really think of binary search or two pointer here. Okay. I hope it made some sense to you.
yeah, I got it.
Okay. 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 Great. All right. 2 more minutes and then we'll discuss the solution. Meanwhile, if anybody else has any other ideas, you're free to share. So obviously one hint in solving this problem is that this is a session on dynamic programming. So think in terms of dynamic programming, right? So just take 1 or 2 more minutes to think about how you can use dynamic programming in this problem. Although it's in general not a good way to just force concepts to be used in a problem, but here the constraints do suggest that a dynamic programming solution might be coming in, right? So yeah, think about some kind of DP states that you can apply in this problem.
Hello.
Yeah, hi.
Can we say that because the expression like we have to find the maximum cost of some subarray,
Right.
and anyways if r minus l plus 1 becomes like greater than m,
Mm-hmm.
so we have to minus that cost.
Right. Right.
So we can just harness the power of m, that r
Mm-hmm.
minus l plus 1 should be like less than equal to 10 maybe, or basically less
Okay.
than equal to m. And somewhere I can think of some L or RDP. I just don't like can't reach there, but this is what I can think of right now.
Nice effort here. Like you are kind of close to the solution, but still just a little bit far away. So I think you guys have taken enough time. Let's just go ahead and now discuss the solution. So the thing is that in these problems, just try to think about what this target function is that we want to minimize or maximize, and just try to investigate how this function is changing, when and where this function is changing, and you will often end up at conclusions. Sometimes the conclusions which Raj just shared, sometimes the conclusion would be that the subarray size would never be greater than or equal to some small number like 10, uh, which happens quite a lot of times, but unfortunately is not happening here. So let's see what exactly is going on here. Okay. So yeah, let's start with the solution. Solution. So let's call the target function as the value of a subarray. So the value of a subarray from L to R is nothing but the sum of all the elements minus k times the seeding of R minus L plus 1 divided by M. Okay. So what we'll do is let's analyze this second part. So let's analyze ceiling of R minus L plus 1 divided by M. Let's see how this function is changing. So what happens is that let's just assume that M is equal to 10. It doesn't really matter. It can be anything from 1 to 10, but for convenience, let's just assume M is equal to 10. So for all values of R minus L plus 1, so the length of the subarray, so for all values of the length of the subarray from 1 to 10, this ceiling function is going to be equal to 1. Okay. And for length from 11 to 20, it's going to be 2. Similarly, from 21 to 30, it's going to be 3 and so on. Okay. So from 21 to 30, it's going to be 3 and so on. So what we notice from here is that the value of this function stays constant for m terms, and then it increases by 1. Okay. So for every subarray whose length is from 1 to 10, the value of this function is 1. So we'll be subtracting k times 1 from its sum. Similarly, if the length of the subarray is between 11 to 20, we'll be subtracting 2 times k from its sum, so on and so forth. Okay. So yeah, uh, does anybody have any doubts until here, or is it clear? I can go ahead. Yeah, looks like it's clear. So yeah, that's cool. So now what we can say is that all that we are interested in is what is the length of our subarray. Okay. and we need to find out some kind of a DP state. So let's now just talk about a blanket rule in problems like these. So when the value of a parameter is quite small, you can think about a DP with the remainder of something with that small parameter as your DP state. Okay. So I'll just reiterate what I've written here. So when the value of a parameter is quite small, which is the case here m is 10, which is quite small. So we can always think about some kind of a DP in which the remainder of something is taken with that small parameter. Okay. So this is a very big hint. So now can anybody think about some kind of a DP state here? So this is like the major hint in this problem. And yeah, so this should point you to the right direction. The thing is that this function is changing every m values. Like for every m increases in the length of the subarray, this function just increases by 1. So all we are really interested in is kind of just the remainder with m. And as and when that remainder hits 0, in the next turn when we add one more element to our array, the value of this function is going to increase. Okay. So that's again a very big hint to figure out the DP state. So let's talk about the DP state. So I'll just give one more minute to you guys to think about some kind of a DP state. And if you can, then you are free to share. So yeah, any ideas in mind? All right, cool. So let me just write down what the DP state is going to look like and see if you guys can comprehend it. So I'm thinking about a DP state where DPij denotes the maximum value of a subarray that ends at index I and whose length leaves a remainder of j with m. Okay. So this is going to be my DP state. So the DP state is simple. It's going to be the maximum value of a subarray that ends at index I and the length of that subarray leaves a remainder of j with m. Okay, so we know that the first dimension can take n values and the second dimension can take m values, and the total is around 3 into 10 to the power 6, which is quite all right in terms of memory. Cool. So is everybody clear with this DP state? If you guys are clear, let's just write it down in the chat, or you can just unmute and say that it is clear so that I can just move on. So it's the maximum value of a subarray that ends at index I and whose length leaves a remainder of j with m. By value, what I mean is the value of that target function.
Hello, Via.
Yeah.
Am I audible?
Yes, yes, you are.
In this question for second state, like for the j variable, can't
Yes,
we do
yes.
something like the actual length? Like,
Mm-hmm. Yeah, of
I
course.
mean,
We
like,
can. Yeah.
what is the importance of this remainder only? Because if the length is there, then we can make the states like the length will be m by 10, means n by m. So total length by m
So
means
the
these will
thing
be the
the
total
the thing is
states.
that the length is quite big, right? So the length of a subarray can be as long as 3 into 10 to the power 5. In that case, the second dimension also takes 3 into 10 to the power 5 space, and the DP table becomes n cross n, right? And n cross n is quite big. It is like 9 into 10 to the power 10, which is like impossible in terms of time limit as well as memory limit. In fact, that's the only challenge of this problem. If a quadratic solution was allowed, then we can just iterate over all the subarrays and use prefix sums to just find out the value of the function over all the subarrays and be done with it. But unfortunately, that's something we can't do. We have to solve this problem in linear time. And what you are suggesting will take quadratic time, also quadratic memory, which is not allowed. Okay. Am I clear now, Rishabh?
Okay. Yeah. But actually, I just want to know, like, uh, if we want to do this problem, then like keeping that only the means the remainder.
Right.
If we think about it, then it looks an intuitive kind of sense, like only
Yeah,
then.
yeah. So that's the challenge. That's the challenging part of this problem, right? In fact, in every code forces problem, the challenge is to think about something which is counterintuitive, something which is not coming to the mind when you just simply read the problem, right? That's the challenge of the problem. You need to think about something smart, doing something that will still do your job, but it would be fast enough. That's all competitive programming is all about.
Yeah. Okay. Fine.
And the beautiful thing here is that if we simply take the remainder with m, our life becomes very easy because we only need the remainder with m. As you have seen how this function behaves is, if we know the remainder with m, and if we know that the remainder is not 0, and if we try to increase the length of the array, then we know that we don't really need to subtract anything else. But if we know that the remainder is 0, then that means that when we try to add another element to our subarray, then we need to subtract an extra value of k. Cool. So yeah, does anybody else have any doubts or is everything clear? If everything is clear, I highly encourage you to just say that it is clear, or you can just write it in the chat. All right, cool. So it looks like everybody is following up. So yeah, this is the state of the DP. Now let's just quickly talk about the transitions, and then I'll just quickly code it up to see that everything works as expected. So yeah, let's talk about what we can do if we know the value of dpij. So let's just write down the transitions. So basically the plan is to use the value of dpij to update the future values. This is actually called as push dp, in which you use a present value to update a future value. And in pull dp, what you do is you try to find out the value of dpij using previously calculated values, for example dpi minus 1, j minus 1, something like that. Okay. Cool. So the transitions are going to be simple. So if we are at dpij, what we can do is we can take the I plus 1th element. Okay. So essentially, if we are at dpij, we know that currently we have a subarray which ends at the index I and it leaves a remainder of j when we divide it by m. Okay. So yeah, that is what's going on. So essentially what happens is when we are at ij, we have two choices. We can take the I plus 1th element into our subarray, or we choose not to do it. Okay, so essentially we'll just form two cases. So case 1 is when j is not equal to 0, and case 2 is simply when j is equal to 0. So let's see what happens when j is not equal to 0. So when j is not equal to 0, essentially we just have a subarray which ends at the index I, and the length of that subarray leaves a non-zero remainder with m. So that means if we try to add another element to the subarray, we don't really need to subtract anything else because this function only increases when the remainder is 0. As you can see, the remainder was 0 and then we add another element, so the remainder will become 1. Similarly, if the length was 10 and we add another element, the length becomes 11 and so the remainder becomes 1. And that is when this function increases in value. So if the remainder is non-zero, then that means that we don't really need to subtract anything else. Okay, so what happens is that from dpij, we can go to dpi plus 1. Okay, and the new remainder is going to be j plus 1. For clarity, let's just write it j plus 1 modulo m. In fact, it will be j plus 1 only because we know that j is non-zero. Okay, so that will be nothing but maximum of course, dp I plus 1 j plus 1, basically itself modulo m. And what we'll do is we'll take this dp value dp ij and we'll simply add a of I plus 1. So all that I'm trying to say here is that I had a subarray which ended at I and its length left a remainder of j. So I just expanded that subarray and now I have a subarray which ends at the index I plus 1 and it leaves a remainder of j plus 1. But I don't really need to subtract anything because we know that this function is not changing values here. Okay, so that's the transition when j is non-zero. So if j is not 0, then this happens. So case 2 is when j is equal to 0. So now if j is equal to 0, what happens is that we know that when we will add a new element to our subarray, then essentially what will happen is that this function will increase in value. Okay, so this function will increase by 1, which means that we need to decrease the target function by k. So the transition will be almost the same as here, but it will simply just have a minus k term. So if j is equal to 0, we can just write down a of I plus 1 minus k. And that is essentially all. Okay. Also, there is one extra case. One extra case here is that the subarray that ends at I plus 1 is actually just the singleton element I plus 1. So that will be dp I plus 1 1 is going to be a of I plus 1 minus k, because the value from 1 to 10 is equal to 1. Okay. So these are just the three things that we need to do. So the first case is when j is not equal to 0. In that case, we can simply add a of I plus 1 and not subtract anything. The second case is when j is equal to 0. So in that case, we will have to subtract a k. And this is just for the case when the subarray that ends at I plus 1 is a singleton element. So in that case, we can just write that dp I plus 1 1 is obviously going to be at least a of I plus 1 minus k. Okay. Actually, it should be max of itself, comma this value. Cool. So this here will be dp I plus 1 1. Cool. So these are the transitions. That's it. So this might be a little bit confusing, but I hope I have done a good job in explaining what all these transitions are meaning. So yeah, if you guys have any doubts in understanding, now is the time to ask them, or else I'll just go ahead and quickly code it up.
Hello.
Yeah.
Could you just explain the transitions once more?
Yeah. Okay. So let's see. So again, if you look at this function, what this function is doing is just look at this r minus l plus 1 divided by m. So when this value r minus l plus 1 is from 1 to 10, its value is 1. When this is from 11 to 20, it jumps to 2 and stays constant for all these 10 values. So if you just take the remainder with m, when the remainder is between 1 to 9 and you try to add a new element, then the value will not change, it will stay 1. But as soon as you add the 11th element, as soon as the remainder goes from 0 to 1, then the value of this function changes. Okay. So as you can see, when the value is 20, the value of length is 20, ceiling of r minus l plus 1 by m is 2. But as soon as you add another element and the length becomes 21, then this function becomes 3. So the main point here is that when the remainder goes from 0 to 1, that is the only case where the value of this ceiling function increases. Okay. So yeah, so what happens is we are at dpij. Okay, and we are going we have a subarray that ends at the index I and its length leaves a remainder of j when divided by m. And now we are trying to expand this subarray to end at the index I plus 1. Now, obviously, when the subarray ends at I plus 1, then it will leave a remainder of j plus 1 modulo m, because we are expanding a subarray that leaves a remainder of j. So if we just add another element, then the remainder will become j plus 1 modulo m. So the first case is when j is not equal to 0. So as you have seen earlier, when j is not equal to 0 and you go from j to j plus 1, so let's say you go from 1 to 2. In that case, the value of this function will remain 1. So if you were previously subtracting k, then you will still subtract k and nothing extra. So that's case 1. So you can just say dp I plus 1 j plus 1 modulo m is equal to max of itself and dp ij plus a of I plus 1. So you are essentially just adding a of I plus 1 and you're not subtracting anything extra. That is because the remainder was not 0. And if you are not going from 0 to 1, then that's fine. You don't need to explicitly subtract anything else. Okay. And now we have case 2. So case 2 is again very similar. Now the only difference is that here j is equal to 0. So if j is equal to 0, as you can see, when we go from 10 to 11, then the value changes from 1 to 2. So if previously we were subtracting k, now we will subtract 2k. Okay, so that's what I've done here. So if j is equal to 0, then dp I plus 1 j plus 1 modulo m. This j plus 1 modulo m will always be 1, but just for clarity I have written this as j plus 1 modulo m. It's going to be max of itself and dpij plus a of I plus 1, and this minus k term because we are going from 0 to 1. Okay. And finally, this third term is just to make sure that if we only take a singleton array, in the case we are not expanding our subarray from I to I plus 1 and we are only taking the singleton element at I plus 1, then we also need to initialize this as dp I plus 1 1 is equal to max of itself and a of I plus 1 minus k. You can say that this is kind of like a base case. So we can just get it done before we start with our loops, or we can do it in between as well. It doesn't really matter. Okay, so this is kind of like a base case. So yeah, is it a bit more clear now, Soumya?
Yeah, yeah.
Cool, cool. Uh, does anybody else have any other doubts? So shall I just go ahead and code it up now?
Hello.
Yeah.
So I have a doubt, like not the question in the not in the question, but like how can we just confirm कि it is like post DP or poll DP?
Yeah, so actually, if you see what I'm doing here is that I'm using the value of dpij to update the value of dp I plus 1 and something else. Okay, so essentially I am using a calculated value to update a future value. Okay, that is called push dp. And sometimes you might have seen transitions like this. So dpij is equal to dp I plus 1 j minus 1 plus 2, something like this. Okay, let's say we are talking about something, uh, let's say we are talking about the least lowest LCS problem, let's say. Okay, something like that. So you have seen that in problems like that there are transitions like this. So here what you are doing is you are calculating the value of dpij using a previously calculated value. Okay, let's just say this is I minus 1. Okay, so you are calculating the value of dpij using a value that you have already calculated. So this is called pull dp. And here you have actually calculated the value of dpij and you are updating a future dp value. So this is called push dp. Is it clear now, Smriti?
Oh yes, thank you.
Okay, okay, great. Cool. So yeah, uh, if there are no other doubts, then I guess I can just go ahead and quickly implement this solution. Uh, Also, let me just ask you guys, do you want me to write the code for this problem? It's actually the same as what I have written here. So if not, then I can just move ahead to the second problem, or else I can just write the code. You can just unmute yourself and just tell me, like it will, if it will be beneficial to you, then I'll just write the code. Otherwise, we are just wasting everyone's 5 to 7 minutes. Right. So if nobody will say anything, then I'll just assume that nobody wants me to write the code. Cool. So I guess we can go ahead and skip the code for this problem. It it will actually give us more time to discuss the next problem, which I think is actually a more interesting problem. All right. So I think with that we have come to the end of the first problem. Now let's discuss the second problem. I hope you guys have already tried that. So the second problem is called flood fill. So yeah, we are at problem 2 for the day, which is flood fill. Cool. Let's just go ahead and read the problem statement. So the problem statement goes like this. So you basically have a line of n colored segments in a row, n colored squares. The squares are numbered from 1 to n from left to right, and the ith square initially has a color of Ci. So two squares I and j, they belong to the same connected component if all the squares from I to j have the same color. Okay, so that's what this line means. So two squares are in the same connected component if all the squares from I to j have the same color. Cool. So now you are playing a game Floodfill, and the game is played as follows. So at the start of the game, you will arbitrarily be picking any starting square. So this can be any square from 1 to n. Okay, and then what happens is that you take turns, and in each game turn, you will simply change the color of the connected component which contains the starting square to any other color. Okay, so you will pick a starting square, and that starting square will just remain for the entirety of the game that you are playing. And then essentially you'll start taking turns, and in each turn you will choose the connected component uh, of the initial square that you had picked, and then you can change the color of that connected component to any other color. Okay, now if you keep playing this game optimally, you need to find the minimum number of turns that are needed so that the entire line can be changed to a single color. Okay, it's obviously always possible to do that. Yeah, I hope the problem statement is clear. Again, the constraints here are interesting. The value of n is up to 5000. So yeah, that might be some kind of a clue here. So if anybody else has any doubts in understanding the problem statement, you are free to ask. Otherwise, I'll give you guys 5 to 6 minutes to just think about a solution. Okay. Yeah, if anybody again has any ideas or any approaches, as and when you get them, you are free to speak. So yeah. So I'll just give one small hint. So somebody mentioned about the concept that is being used in this problem when we were discussing the solution to the previous problem. So maybe that might be some kind of a hint to you guys. Of course, try to look at the constraints and think about some kind of a DP solution. I mean, I'm not forcing DP here in this problem because I think anybody who reads such a problem would think of DP as a first step here. So yeah, try to think about some kind of a DP state. In fact, even before you try to think of DP states, try to just analyze the game and try to see what's going on in the game. That will essentially help you to form a DP state. So the main thing here is that in problems like these, I mean, in mostly all the code forces problems, the main idea is to not just think about, just read the problem and think of a DP state. That is something that you should do in a lead code problem. What we should do in a code forces problem is to just analyze what we are doing in the problem, analyze what's going on in the problem, and then think of some observation which can help you apply DP. Okay, straightforward DP problems are very, very rare these days. In most of the problems, you have to make some preliminary observations and then you come to some conclusions which allow you to use DP. Okay. So yeah, that's what is going to happen in this problem. So I'll give you guys 3 4 minutes to think. And meanwhile, if you have any approaches, just feel free to unmute yourself. All right. Any observations or any ideas? I mean, I'm not really expecting you to just think of the entire solution, but any observations that you've done till now, anything that might be helpful in solving the problem?
It can also be solved using the connected graph solution. Okay, it is similar to the to a connected graph.
Okay. Yeah, makes sense. The thing here is that try to just simulate the game. Okay, try to take a small subarray and simulate what happens, and then you will realize that there is something very familiar going on here. So let me just ask this problem. So can anybody tell me what will be the final color? So think about this final color. Okay. So we need to find out the minimum number of turns needed for the entire array to be changed to a single color, right? So can anybody tell me what that final color is going to be? It's actually not very hard to say.
The color at
The
the
first color
corners.
that we do.
Sorry, can you just
The
repeat?
color at the corner.
Exactly, exactly. So the main observation here is the final color is going to be either A1, so let's call it C1. So the final color is either going to be C1 or Cn. So this is the main observation in this problem, and let's see why that happens. So let's just start with the solution and let's see why the final color is going to be either C1 or Cn. Okay, cool. So we have this array, right? And we have some colors. So we have C1, C2, C3, C4, C5, C6. So my claim is that when the game is over, then the final color is going to be either C1 or C6. So let's say we choose this color C4 as the first color. And obviously, if we don't change C4 to either C3 or C5, then the entire turn is pretty useless, right? Because nothing else just happened in our turn. So let's say we changed it to C5. So then we get C1, C2, C3, C5, again C5, and then C6. Now this is the connected component, and now we can change the color of this entire connected component to something. So let's just say we decide to change it to C3. So then we get C1, C2, C3, 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 C6. Okay. Again, so now let's say we decide to change its color to C2. So we get C1, C2, 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 and C6. So now let's say we decide to change it to C6. So we'll get C1, C6, 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 and C6. And finally, we are left with just one option, which is to change it to C1. So as you can see, in any game, whatever happens, the final state is going to be either just the first color repeated n times or the last color repeated n times. Okay. So does anybody else have any doubts in understanding what I have just written here? The main claim that the final color is going to be either C1 or Cn. Is everybody with me with this observation? Because the only thing we can do is to change the color of the connected component in which our initial ball was, our initial color was. So the initial color can only move one to the left or one to the left, one to the right. And finally, it has to end up at either C1 or Cn. Okay, cool. Right. So with this hint in mind, try to think of some kind of a DP state. So this is the observation that will allow us to use DP in this problem. Anybody having any ideas?
Either index, first color or last color.
Right, right. So that's something that we can include in the DP state.
L2R.
Awesome, awesome. So Jatin has actually said out the
Hello, uh, you are in mute actually.
oops, sorry. So what I was saying was that Jatin has actually said out the correct DP states that we'll be using. So the DP states are going to be something like DPLR2. Okay. So what DPLR0 will represent is that DPLR0 is going to be the minimum number of moves to clear out the subarray from L to R such that the final color of the subarray is going to be C of L. Okay. So the minimum number of moves to cover the entire subarray. By covering the subarray, what I mean is that making sure that all the elements have the same color from L to R such that the final color of all cells is C of L. Okay. And similarly, DPLR1 is the same thing, but the final color is going to be C of R. So is everybody clear with this DP state, with the definition of this DP? Or does anybody else have any doubts here? All right, cool. So yeah, this is actually known as range DP. So this kind of a DP is typically known as range DP. So range DP is essentially when you try to apply DP on some kind of a range. And here you can see that we are dealing with a range from L to R. And we also have an extra component, extra dimension to our DP, which is just a Boolean variable from 0 to 1. So it is 0 when the final color of all the squares is C of L and it is 1 otherwise. Okay. So this is actually called as range DP. Cool. So now let's just look at the transitions. Before we even look at the transitions, another thing that we can do is that we can remove, essentially remove elements which are contiguous and have the same color from the subarray. So we can remove elements. So we can remove continuous elements having the same color from the subarray. So what this means is, let's say that this array was 1 1 1 1 and 2, then we can just say that that is the same thing as the array being 1 2, because all these ones are like they are initially in the same connected component, they're already in the same connected component. So we can just kind of compress this array to remove these kinds of duplicates. Okay. So I hope this is clear. So essentially what I'm saying is that if there are already connected components with length greater than 1, then we can just compress that and find another array that has the length of all the connected components as 1. That will just make our implementation easier. That's not something that is necessary, but I'll just assume that we have done that. So that will just make our transitions pretty easy. So now let's look at transitions. By the way, I hope that everyone is clear why we can do this. We can do this because these are already in the same connected component and they will always stay in the same connected component. So instead of having, let's say, all these ones here, we can just have just a single one. Good. So now let's look at the transitions. Cool. So let's try to find out the value of dpij0 and then we'll try to find out the value of dpij1. So this time I am doing a normal pull dp, not some fancy push dp, something like that. So what is dpij0? So for dpij0, we will just take two cases. So case one is that, so yeah, what we are trying to do is we have a subarray from I to j, and we want to make all the elements have the color equal to C of I. Okay, so there are essentially two cases. So the first case is when we get dpij0. So we get dpij0 from dpi plus 1 j0. So what this means is that we have already covered all the elements from I plus 1 to j, and the color of all those elements is C of I plus 1. And now we are expanding that covered subarray to I to j, right? So we have a subarray from I plus 1 to j. It is already having all the elements as the same value. And then we are doing one more operation to expand that subarray from I plus 1 j to ij. Okay. So the transition there is going to be simple. It's going to be dpij0 is going to be nothing but a minimum of itself. I'll just write itself here. And that's going to be dpi plus 1 j0 plus 1. Now, why is this plus 1 here? This plus 1 is here because the color of C of I and C of I plus 1 will always be different, because I have already removed duplicates from this array. So that means the entire subarray from I plus 1 to j is already colored in C of I plus 1. So I will have to change that color to C of I. So I'll just write it down. So dpi plus 1 j0 implies that the subarray from I plus 1 to j has color C of I plus 1, but we already know that C of I is not equal to C of I plus 1. Hence we will add 1. Hence we will do one more step. Okay, so I hope this is clear now. So again, we are simply using the observation that if we have a subarray covered, then all the colors in all the cells of that subarray will be either of the leftmost cell or the rightmost cell. So here, if we are going from dpi plus 1 j0, then that means that the color of all the cells from I plus 1 to j are equal to that of the leftmost cell, which is C of I plus 1. And we know that Ci is not equal to Ci plus 1. So we need one more step to convert that to Ci. Okay. So now all the cells in I plus 1 to j, which were originally C of I plus 1, will be just converted to Ci in one step. Cool. So that is case 1. So cool. Now let's go to case 2. So case 2 is that we get dp ij0 from dp ij minus 1. Sorry, no, from dp I plus 1 j 1. Again, so we can get it from either dp I plus 1 j0, or we can get it from I plus 1 j1. Right. So now, can anybody tell me what will happen now?
We will increase by 1.
So here's the thing, like in the first case, we knew that C of I will never be equal to C of I plus 1. So we will simply increase by 1. But in this case, we will have to check whether we increase it by 1 or not. So what will be the condition in which we will increase it by 1, and when will we not increase it by 1? Can anybody tell me that?
So ICI and CJ are equal.
Exactly. So if Ci is equal to Cj, then we don't really need to increase it by 1, right? Because the color of all the cells from I plus 1 to j is now equal to Cj, the rightmost bound. So let's say we have a variable add, which is equal to 1 if Ci is equal to Cj, something like this. So a better way to write it would be if Ci is equal to Cj, then add is going to be equal to 1. Sorry, then it's going to be equal to 0, otherwise it's going to be equal to 1. So then we can simply write dp ij0 is min of itself and dp I plus 1 j1 plus add. Okay. So I hope this is clear. So essentially what's going on here is that similar to the previous case, we have a subarray from I plus 1 to j and its color is now equal to C of j because we are dealing with dp I plus 1 j1. And yeah, so if Ci is already equal to Cj, then that means we already have a subarray from I to j which has all the colors as Ci. So that in that case we won't add anything. But if Ci is not equal to Cj, then we'll have to add one. Okay, so that's what this transition is doing. Cool. So yeah, this is how we can find out dpij0, and we can actually do a pretty similar analysis for dpij1. So I'll just quickly write that down. So we'll do case 1. So as we were going from, we were finding dpij0 using the values of dpi plus 1j. Now we'll find dpij1 using the values of dpij minus 1. Because obviously in the last move we are changing the connected component to the color of the value of Cj. Okay, so we'll be using dpij minus 1. I hope that makes sense. So yeah, again here there are two cases. We'll just write them down pretty quickly. So dpij1 is going to be min of itself and dpij minus 1 1 plus 1. Again, we can simply write a plus 1 here because we know that the color of the subarray from I to j minus 1 initially was C of j minus 1, but we have already made sure that Cj minus 1 is never equal to Cj. So we can just write down a plus 1 here. And the second case is when we go from dpij minus 1 0. So in that case, we'll say that dpij1 is min of itself and dp of I j minus 1 0 plus add. And let's just define an add variable here. Again, it would be just the same thing. So if Ci is equal to Cj, it's going to be 0, otherwise it's going to be 1. Again, so what dp ij minus 1 0 means is that we have a subarray from I to j minus 1 and initially all the elements have the color equal to Ci. And now we will have to do one more operation if Ci is not equal to Cj. And if Ci is already equal to Cj, then all the elements in the array already have the same color, right? So in that case, we don't really need to do any other operation. So yeah, these are the transitions and this actually completes the solution to this problem. So if anybody else has any doubts related to these transitions, related to the definition of the DP, anything about this problem, now will be the time to ask them. Wow, so it's good to know that you guys are clear with all this stuff. So it's actually a pretty interesting problem. So yeah, it was actually fun to solve. So with that, I think we have come to the end of everything that I wanted to discuss in this session. So if you guys have any other general doubts, this would be the time to ask them. They may or may not be related to the two problems that we discussed today. And if that's not the case, then I think we can end the session for today.
Hello.
Yeah,
Am I
hi.
audible? So,
Yeah, you are.
thank you for the section chapter. Uh, can you share the like post DP and pole DP any resources we have in the internet?
Yeah, so actually I learned about it from watching, there is a very famous YouTube channel called Galen Colin. So he has done actually some topic streams and I watched two of his topic streams from dynamic programming. So that is where I learned about this push DP and pull DP, and it has actually helped me quite a lot because implementing push DP sometimes can be very, very easy as compared to pull DP. So yeah, you can watch those topic streams. They are quite big, but in the end, they will be quite helpful to you.
Oh, thank you. I know Galen Collin actually.
Okay, okay, great. All right. If there are any other doubts, then you can ask me. Otherwise, we can end the session for today. Okay, then thank you guys for joining. And I'll probably be taking another session discussing something else, something new, maybe solving some more problems or maybe teaching some concept. And it will probably be happening on Monday. Okay. So, yeah, that is it from my side for today. Uh, See you guys on Monday. Thank you so much for joining.
Thank you.
Thank you.
Yeah.